Yeah, we're going to talk about reflection and code generation in C++. I asked the Midjourney AI to generate a picture of reflection in C++, and this is what it came up with. So interestingly, I could not make it generate the plus signs after the C. So it's just a C, not a C++. That's, I guess, a metaphor for poor code generation in C++. Also, the reflections are kind of wonky and out of place sometimes. That's also a metaphor for reflection being kind of wonky in C++. But what can you do? So this talk is going to have a lot of code. I'm going to throw a lot of code at you. Clicker is not working. Okay, there you go. I'm going to throw a lot of code at you. So if you can't read the code, or if the code is hard to read, or if you have a question about the code, feel free to interrupt. We're going to talk about a simplified version of a real world problem that I had when making a compiler. So we're going to talk about the diagnostic system in this compiler. So let's start off with a unused variable warning. We're going to represent it as a struct here. And when you have a warning in a compiler, you want to locate it. You want to have a location information when you print out the diagnostic. So we have a variable for the location. And we need to have a way to report the diagnostics. So we have a diagnostic reporter with a report method for that diagnostic type. And this is an abstract base class because we can have different ways of generating, of reporting the diagnostics. So for example, we might have a CLI-based diagnostic reporter, which prints to the terminal. So here we have a println call where we print out the location information, and we print out a message, and we also have a severity component. And we might have a JSON-based reporter. So same thing, we report the location. Here we're using a custom format specifier. The details aren't important for this talk, but just thought I would throw that in there. We also have the message in the JSON reporter, and we also have the severity. And notice that the message and the severity are duplicated. We don't like the duplication. We'll factor that out in a bit. So in the base class of the diagnostic reporter, we also want to have categories for each diagnostic. We want to be able to enable or disable categories as a user option. So at the bottom, we have a list of disabled categories. And whenever we want to report a diagnostic, we check if the category for the diagnostic is inside of that disabled category list. Now, we don't want to have each method in the CLI reporter and the JSON reporter and the whatever else reporters. We don't want to have each one of those check for containment in the disabled categories. So we put the common code up here in the base class, and we wrap each of the report methods. So now the public interface is calling this report method that checks the diagnostic category, and the implementation is a virtual method still. Now, on the slide, it's all public, but in practice, you'd make the report impl function protected, but slideware. Now, I'm adding these might seem weird things that I'm doing. The thing that I'm doing is not important. It's not important that I have categories in severity and message. I'm just setting up a code example that is complicated enough that simple techniques won't work effectively. So we have to bring out more complicated techniques, and I'll talk about that. So here's all the code that we've made so far. On the left is the base class and also the diagnostic type. And on the right is the CLI diagnostic reporter and the JSON-based diagnostic reporter. Now, this is all for one diagnostic. If we want to add a new diagnostic, we have to put code in 5 different spots. One, we have to make the diagnostic type to store the information about that diagnostic. We have to make a method in the diagnostic reporter base class to do the filtering based on the disabled categories. We have to make the virtual function, the pure virtual function. We have to make an implementation in the CLI diagnostic reporter and also an implementation in the JSON diagnostic reporter. So our goal is to make this less of a pain to add new diagnostics. Right now it's 5 spots. If you add more kinds of reporters, for example, you might have an LSP-based one or an Emacs-based one or something for WebAssembly or whatever, you can imagine a lot more kinds of diagnostic reporters. We don't want to add methods for each version every time we add a new kind of error in our code base. So what we want is actually a nice, concise syntax like this, where we have more of a declarative style for defining things rather than having a bunch of code strewn around. So this is the end state. We're not going to get there in one step. It'll take a lot of steps to get here. And this example uses C++ attributes. You can, well, we'll talk about that later. So in this talk, we're going to cover a few things. We're going to talk about Sphere and concepts, and they're actually very similar, basically the same thing. We're going to talk about macros and templates, which are also basically the same thing. Macros and templates are for generating code. Sphere and concepts are for reflecting on code, looking at code. And we're also going to look at ASTs and regexes, which are also the same thing. You'll see. And this is also a reflection technique. So looking at the report functions in our CLI reporter, we have the messages here. So this is assuming we have another diagnostic type called diag unexpected token. So we have unused variable unexpected token. They have the messages there. And remember, the messages are inside of each report implementation. So the JSON functions also have the same strings. So we don't want to duplicate the string in every place, because if you fix a typo in one, we have to fix a typo in all of them. You have to remember to fix a typo. So let's factor the strings into the diagnostic class itself. We're going to use a function here called message, and we just call the message function. And we could do the exact same thing with the severity. So here we have the severity of warning. We could throw that into a function. And the different diagnostic types can have different variables. So like here, the variable is called variable. And the other diagnostic for unexpected token, it's called a token. But we want our report functions to look the same. So let's change this variable and factor that out into a function as well. We'll call it location. And now we have a report impl function, which if we do the same process of factoring for the other report impl function for the unexpected token, you'll notice the bodies of these two functions are identical. They're token for token identical. The only difference between these two functions is the parameter type. And if you have two functions with an identical body in the same parameter type, then what you can do is use a template, right? So now whenever you call report impl, C++ will create an instantiation of the template, fill in the type for you, and then it will call the appropriate location, message, and severity functions. But when we do this, there's a problem. The compiler complains because our function's a virtual function. It's not, because it's a virtual function, it can't be a template. Templates and virtual functions don't play nice together. So we can't actually do this technique. Well, actually, we can if we make report impl. And this is just a normal function. It's not a virtual function. Well, it's a template. It's not a virtual function. And we call that from our virtual functions. So it's a little better because we're not copy pasting the println code, but we still have to write out all of the different overrides, all the different virtual functions. So it's an improvement to what we had originally. It's still not ideal. So we've covered using templates to generate some code. It's not 100%, but it's progress. So let's add some more complexity. And the more complexity will add constraints and make things more complicated. So we'll have to do more tricks to work around the complication. So in a real compiler, you don't usually just have one message. You might have a message and associated information. here we have a type mismatch error. So if you're calling a function and you're giving it a string, but the function takes an integer, the compiler should tell you, hey, here's the thing you were passing in, that's a string, but the function is taking an integer, and you want to point them to both locations, point the user to both locations. So how would we represent this in the compiler? Well, we would have two source location variables, one for each diagnostic message inside of our type mismatch struct. And then for the type names, those are runtime as well. So those need to be string views, for example, or some internal type, but we'll just use string views for this example. So now the report impl function is a bit more complicated. We have two println calls, not just one println call. And the first println call doesn't just have one parameter of the format, it has two parameters, one for the location and another for the type information. And the second call has basically the same thing. So it's a little more complicated than just location and a hard-coded string, like in the previous diagnostics. So we would like our report impl function. Oh, yeah, sorry. Before we get to that, let's do the same thing we did before and factor these guys out into methods in the class. So we factored out message, severity, and the location. And notice the message doesn't just return a string, it returns a format of a string. That's why I made message a function and not just like a static variable. So that factored out the first print's message and location and severity. The second print, what do we do about this? Our message function, our current thinking is that message just returns a string, not a list of strings. Here, I'm just going to make a message to and location to. We don't expect this compiler to have a bunch of different permutations. So, just make more methods and put 2 at the end. But for our report impl function, this only uses location and message. It doesn't use location to and message to. What we would like is to throw in location to and message to. But the problem is, if you give in the unused variable warning to this function, it'll fail to compile because unused variable doesn't have a second location and a second message. So how do we make it compile the code both ways? Well, we can move the thing that doesn't compile into its own function. Like here, we'll call it report impl2. Great names. It'll simplify it down eventually, but slideware. So we make a separate function, but this still doesn't work because when we call report impl2, report impl2 will fail to compile if you have no location to and message to. So what we could do is use a technique called svine. Svine is a trick to turn on or off different function overloads. So what we want to do is turn off this overload if you don't have location to, or in other words, only allow calling report impl2 if you have a location to. So we do that with this ugly svine stuff. There's like 50 svine tricks. I just picked one here. This trick works by you create an instance of the type. In this, it's called diag. Use decoval to create an instance. This is only a compile time, so it's not a runtime instance. And then with that instance, we try to call the location to method. If this fails to compile, then because of how C++ works and the syntax we used, it's as if this function doesn't exist. But if the function doesn't exist, then the call up on the top, it doesn't work. We don't have a function to call. That's when you make an overload that you can call. Where does that go? You make an overload that you can call. In this case, when location 2 is missing, we just call this empty function. So in the case where we don't have location 2, all we're doing is the println, the first println, and then we're calling an empty function, which does nothing. But in the case where we do have a location to, it's going to call the first version of report impl2. Actually, it doesn't do that because both of the overloads for report impl2 are valid. Both of them exist if you have a location to. So we need to disable the bottom one. And if you remember in std vector, there's like a bunch of methods like data, and data works const and non-const. If you call data with a non-const vector, you get a non-const pointer back. If you call data with a const vector, you get a const pointer back. C++ will prefer to call the non-const version if it's available, and if the non-const version isn't there, it'll call the const version. So we can use that priority mechanism to make the bottom one have lower priority than the top one. And you can imagine this takes a lot of time to actually write, and it is definitely not maintainable, but it works. So this is what gives C++ a reputation for being terrible for reflection. All this template metaprogramming is FINE stuff. But this has worked since probably C++ 11, maybe before, I don't know. So if you're on an older compile, I mean, println doesn't work, but all the other stuff, this FINE stuff will work on older compilers. But let's say you're a sane person and you are repulsed by this. What can you do? Well, what we would like is the printlns to be right next to each other and in the same function. But how do we do this? We want to write like an if statement, but there's no if statements, both sides of the if and the else, or, it needs to compile. So we can't use a normal if statement, but we can use an if const expr. If const expr says if the magic is false, then it doesn't need to compile the body of the if. So how do we implement the magic? Well, we can use the exact same stuff we did, but instead of doing the work of printing in the helper function, we just return true or false. So in the case we have location 2, we return true from our hasLocation2 function. And otherwise, in the const version, the fallback, it returns false. So the calling code is much simpler now. We say if const expr, and it say hasLocation2. It's pretty readable. It's saying, do we have a location2 method? If so, use a location2 method. And the bottom code, we can throw that in some header file and not look at it, hopefully. Maybe add a bunch of comments. But the business logic of printing isn't mixed in with the weird C++ reflection stuff. So it's nice and separated. But there's a way better way to do this since C++20. Let's throw that code away and let's use C++ concepts. That requires, there's a bunch of things that concepts. My favorite one is the requires expression. So requires returns a Boolean. I mean, it requires is an overloaded keyword. It means like 50 things, but requires in this case is a compiler magic which says, hey, does this code compile? If it compiles, returns true. If it doesn't compile, return false. So if calling .location2 succeeds in terms of compiling, then it'll emit the code for println, the second println. Otherwise, it doesn't. Yes? Is requires the same as enable if? No. Because enable if, the thing you get out of enable if is a type. The thing you get out of requires is a Boolean. Enable if, you give it a Boolean and it gives you back a type. Concepts, you can give it, I guess, anything really, and then it gives you back a Boolean. I was not able to get this working with enable if, but I didn't try very hard. Maybe there's a way to do it with enable if. I imagine you would need to use other SVNA tricks as well, and it would just get hideous. Requires is a much simpler mechanism for this. So hats off to the people who made C++20. I hate concepts generally as a feature, but this stuff for metaprogramming is very nice. So we talked about sphenae and we talked about concepts, which, as we saw, are basically the same thing. Okay. So here's the code so far. The code on the top is what we were working with. The code on the bottom is all those overloads, those virtual functions that call into the template. Let's address these overloads here. Now, the only thing different between these overloads is the parameter. And before we used a template, but you can't use templates with virtual functions, right? But what we can do, instead of using a template to generate code, is use a macro to generate code. So let's make a macro for the report impl implementation. Call it make report impl, and just call it 3 times, 1 for each method. I know people hate macros, but you got to do what you got to do. Now here's the base class. So we were looking at the implementations like the CLI reporter. Here's the base class. Let's factor out the category into a variable. I'm not going to show all the details for that. But now we have some duplicated code here. We can make a template. We already showed you another example of that. This is the same thing. But now we have these virtual functions at the bottom. Let's make a macro for those. Same macro we made, except this time, instead of doing override with a body, this is equals 0 at the end. So now at the top, we have the base class code that generates the report impl pure virtual methods. And at the bottom, we have the implementations. And you notice there's some common code there. So let's deduplicate the common code by using a macro. We're going to call it diagnostic types X. And we can, there's a definition. All it does is those 3 lines of calling make report impl 3 times. Now, this kind of hurts your brain for a little bit because when we make the macro, we don't have anything called make report impl. It's only after we define diagnostic types X, when you use it, that we have a thing called make report impl. And make report impl changes across the code. So this is kind of like higher order functions, higher order macros in C++. It's a pretty useful tool. This specific way of doing it is called X macros. It's a common pattern. Well, hopefully not too common, but yeah, so you can use X macros. I often use this to deduplicate lists of things. You can use this to generate enums and also string functions for the enums or parsing function for the enums. Yep. Yes, we are undefining a macro and redefining it with a different definition. Yes. For make report impl. Now, we were doing that before we made the macro. We were doing it already here. I mean, you could have chosen different names here, but I chose the same name so we could very easily make it a macro. Now, if they were different names, you can just refactor it to be the same name and be careful you don't mix them up. Okay. So that's enough of those macro things. Okay, so here's our diagnostic type so far. It looks pretty lean, but there's still a lot of syntax noise. We'll get to the syntax noise in a bit. But first, what I want to do is split the concerns. So the bottom half is metadata for each diagnostic, and that's only used by the reporting code. And the top half is used by our parser or analyzer, stuff like that. So I want to keep them kind of separate. And also, ultimately, we want to generate the metadata from the top code. So we want them separate for a few reasons. So let's separate them into 2 different classes. So we keep the top as the diag unused variable, but then we make this class called info. Info is actually a template that you make a specialization for each different diagnostic type. So here we have the specialization for diag unused var. And at the bottom for location, you see we just said return variable. We didn't say return diag.variable. And the way this works is we're inheriting from the diag unused var class. So we're inheriting from the info, the metadata inherits from the diag type. And that gives us, we could just say return variable instead of threading parameters around everywhere. So here's our report impl class in the CLI diag reporter. So to use the new info thing, all we have to do is downcast from the diagnostic type to the implementation, the metadata class. And then all of this will, like the location, if you say info.location, it calls the metadata method for location, and that will get the variable from the diagnostic. Now this downcast is undefined behavior. Don't tell anybody though. Because we didn't create it as an instance of the info, we created it as an instance of the base class. Maybe it's not undefined behavior, I don't know. It works. Works on my machine. And like if you're doing this in production, there's other ways to do it. This is just the easiest to explain, I guess. So here's the metadata for the unused var. Let's focus in on the message and location bits. This is pretty wordy. We have like return and we name a bunch of types and stuff. And I want a much nicer syntax for that. So let's use a macro to make a nicer syntax. The goal here is we're trying to make sort of a domain-specific language for expressing the metadata instead of doing lower level plumbing like create this method, create this method, create this variable. And I like macros. So for the type mismatch diagnostic, though, we don't just have a hard-coded string message, we have extra parameters, and we have to call format. So our diagnostic message macro just takes MSG, one parameter. We need to pass in two things there. So let's use a variadic macro and use vargs into format. Now, if you give format just a string literal, it'll just return the string. You don't need to have a format specifier there. So our previous example works fine. The unused variable example works fine. Sorry? Which, sorry? Third line? Oh, yes. So the third line should say return lock, not just lock. Yeah, my bad. I was too anal about the animations that I didn't look at the code. Okay. So yeah, aside from that bug. And yeah, now we can call diagnostic message with the more complicated message function. Speaking of more complicated diagnostic message functions, we have also that message to thing and the location to thing. But our diagnostic message macro only declares message and location. So we could do some complicated macro stuff, but we have enough of that. So let's just copy paste the macro, make a diagnostic message to which generates message to and location to. This is the pragmatic approach. If you want to do something more complicated, have fun, but I try to make my code not that crazy. So here's what our diag unused var looks like right now when we use the diagnostic and message stuff. Let's use more macros. We're going to put this whole thing in a macro. And we're going to factor things that are specific to this type into this make diagnostic macro. So let's take the name of the diagnostic Make that a macro parameter called type. At the bottom here, we're building a call to the macro. And on the top is the definition of the macro. Now let's take the body of the macro, including the curly brackets, and make that a parameter. Now I included the curly brackets so it looks at the bottom sort of like you're declaring a struct. Without the curly brackets, it doesn't look like you're making structs, so it doesn't look like struct members. And that confuses Clang format, and it also looks weird. So we can take the severity and make that a parameter to our macro. And here I opted to remove the quotes when you call the macro, and you do #sev to add the quotes back. In my production code, it's not actually a string, it's an enum, but I wanted to use a string as an example. We could do the same with category, except we don't use a string here. And we can put the message out as a parameter. And there we go. We have a reusable make diagnostic macro that generates the metadata and the original struct. So here's all three of the example diagnostics: our unused variable, unexpected token, and type mismatch. And we basically made a domain-specific language for making diagnostic types. Domain-specific languages are pretty common in compilers because we're compiler guys. We like making languages, so we make languages for our languages. But I think this looks pretty nice. Well, it doesn't look nice, but it's better than having a bunch of methods strewn about, and it's better than having like 12 lines of crap. We need more macros. So remember the diagnostic types X thing, the X macro we made? The problem with that is that it contains a list of all the diagnostics, the names, and also our make diagnostic calls contain the list of all the diagnostics, right? We have whenever we add a new diagnostic, we have to add it to the make diagnostic list and to the diagnostic types X list. I want to make it easy to add diagnostics. I don't want you to chase a bunch of different files to add a diagnostic. So we'll put all of the make diagnostic calls in a macro. So this whole thing's a macro. Okay, and then the original call to diagnostic types X, these are the original calls to generate the report impl functions. What we'll do instead is we will call our new diagnostic types X macro. And I changed the name of the thing that's called to do diagnostic. Now, do diagnostic gives you the name, and it gives you the body and the severity and the messages and stuff. We don't care about that here. We just care about the type name. So we use ... to ignore all the extra parameters. So now we've successfully made it so that anytime we add a diagnostic, we only have to update this thing instead of updating a bunch of different files. But I mean, come on, macros. We're done with macros. Let's not do macros anymore. We want something like this. This is, in my opinion, much more readable. Also, Clang format doesn't freak out on it, and your static analyzer doesn't freak out on it. And if you get a compiler error because of a typo, you don't get a backtrace of macros. So we definitely want a syntax more like this. Here we're using C++11 attributes to annotate our structs with extra stuff. Now, a good thing about C++ attributes is that compilers ignore them by default. So it's not an error to add an attribute, and you can have a separate tool that looks at the attributes and does stuff. The problem with this code is that this is actually a syntax error. You can't put attributes on a struct. Actually, you can, but it has to go after the struct keyword. So in my opinion, this is a non-starter. This is terrible syntax. I may as well use macros. So I don't know why you have to put the attributes there. So I thought, well, if I can't put them outside the struct, and I don't want to put it in the middle of the first line, I'll put them inside the struct. So here, technically, we're adding attributes to the first member variable of each struct. So we're adding, on the top, we're adding attributes to the variable member, and on the bottom, we're adding it to token, which is fine. We don't need it to be on the struct because our code that looks at the attributes can find them anywhere. The problem is that Clang format doesn't like this code. What it does is it adds some weird staircase indentation, and it puts our variables in the far right of the code. So that's a non-starter. I want it like this. So then I found another hack, which is just add semicolons in random spots. Now, what the semicolons do is the semicolon declares an empty statement in the struct. You can have a bunch of random extra semicolons inside of your struct body. Just like inside of a function, you can have extra semicolons. You could do that inside of your struct. And the attribute is an attribute on the empty statement. So it's super weird, but it works on my machine. So let's do this. But it looks like a bug. So compilers complain. Do you have to shut the compiler up to say, yeah, I know what I'm doing? So you add a bunch of ignore warning things. Okay. So how do we make that code work? Well, we can bring in our good friendly dragon, LLVM. So LVM is a compiler toolchain infrastructure thingy, including Clang. And Clang is a compiler that can read our code. So let's add the feature that we want to Clang. Actually, that's a dumb idea because Clang is never going to accept our application-specific attributes. And even if they did, there's a huge turnaround time. So we have to maintain a fork of Clang. Maintaining a fork of Clang is only something big companies do, really. And I'm one guy. So I'm not doing that. But Clang provides a library interface to the compiler. So let's use the library interface called libclang. So our plan of action is to have libclang find all the classes in our code whose name starts with diag. We find all the statements, those empty statements inside the class. We get the attributes. We extract the information from the attributes, such as attribute name and all those parameters. And then we generate C++ source code. We're going to generate source code for those info, template, and specializations. That's why I split it up into just the struct, which is handwritten code, and the info metadata is the generated code. So to find all the classes, libclang has a convenient cursors API. We don't have to worry about namespaces and nested class, whatever stuff. We could just say find all of the classes that start with diag. And same with statements. We could just quickly find all the statements inside our classes. And same with attributes, except actually libclang does not expose attributes. Libclang doesn't even expose attributes that libclang does understand. So you head over to the documentation and you see, do not use libclang when you want full control over the Clang AST. Now, when I read this originally, I thought it meant things like you want to evaluate things const expert, or you want to rename variables or other advanced things like that. But no, it means if you want to use the Clang AST, don't use this library. Other people have noticed this problem. So Funathan says, libclang features are implemented on demand. Need to get more information about XXX for your project? Implement that yourself. Now, I'm a compiler guy, and I'm totally down to implement it, but I started working on this talk last week, and I'm not going to implement a feature in Clang and upstream it and wait for them to release in a week. I want the features now. So we need to figure out what to do when libclang does not give us the attributes. Well, actually, libclang does give us the attributes. It gives us attributes in a funky format. They're called tokens. If you've written a compiler, you know that you split the source code into a bunch of separate tokens. And what you can do is ask libclang, give me all the tokens inside of the struct. So you can use libclang to find the struct and to split things into tokens. but we will need to manually go through the tokens ourselves and parse everything. It's actually only like 50 lines of code. It's not that complicated, but you wish the compiler would do that for you. So basically, we're just going to look for a left square bracket twice, then the demo, and then the colon colon, and then we write an if statement afterwards saying, what's the next thing after? Is it severity? Is it category? Is it message? And then store that information in your code generator tool. And then you print out everything at the end of your code generation tool. You print out all the metadata, the C++ source code. So libclang has a number of problems, like you need to manually parse the C++ tokens. At least you don't need to tokenize it and run the preprocessor. I mean, I hope you don't use macros with this, but if you did, you would need to run the C preprocessor first and then get the tokens. We don't have to do that. libclang takes care of that, but we still have to parse all the tokens. Installing libclang is also an issue. You have to make sure you have the right version in case an older version didn't have the things you need. You want a newer version, and getting that working, especially for an open source project, getting everybody who uses the open source project on a good libclang version is a pain. And then having your build system find the libclang is also an issue, especially if you support multiple platforms. You have to have documentation for how to do that for all your users. And integrating your code generator tool into your build system is complicated because you don't want to have, every time you add a diagnostic, I don't want to have to manually run the code generator and then run my normal build. I want it to be part of the build so it just magically works. But then you have to worry about things like cross compilation because your code generator doesn't run on your Android device, even if you're compiling an Android project. So you want to run the code generator tool on your build machine, which is a different compiler probably than your target machine. It gets complicated. So there's a lot of drawbacks to libclang. I hope that tools like CMake and Meson and other build systems make it a lot easier, but right now they don't. So there we talked about AST. Let's talk about regexes. So because we had to split up, because we had to kind of parse the things ourselves anyway, and because the syntax is actually pretty simple, why not use regular expressions to extract the information we want? So we just write some basic regular expressions. We allow for some white space just in case somebody types a space or hits new line or whatever. We don't want to crash there or complain. So we allow a bit of white space in some spots, but importantly, we need to capture the word warning. And then we run another regex to get the category, which is basically the same regex. And the message is basically the same thing, except we want to parse the message separate from the location. So we have two capture groups. And the message can contain all sorts of stuff. Like your message can contain commas inside the string. So we have to be a little more careful with the regex here, but it'll work. And then now that we have the individual pieces of metadata, the problem is correlating that, because these are all a bunch of separate regexes. How do you match them to the diagnostic? Well, what you could do is do a regex for the diagnostic, the top, and then find anything, like start your search for these like severity, category, message, start it after the struct, and make sure you don't match the next struct if there's a typo. It gets tricky, but this is actually basically this program that would read using regexes is about as long as libclang, like a code that uses libclang and mainly parses things. And in my opinion, it's a bit more flexible because regexes are really flexible. And it's also a lot simpler to use regexes than to pull in a big dependency for libclang. If you're already using libclang for other reasons, then sure, use it. But regexes, like C++ has standard regex, and also you can avoid cross-compilation problems by using scripting languages. So you can use Python to read your C++ code, like a Python script or a Go script or whatever, and avoid the issues of mixing compilers when cross-compiling. So there's regex. So when would you use reflection and code generation like we talked about? Well, we can use it in a compiler to allow you to add metadata to all your structs. Qt, the UI framework, also does this. So you can annotate your class and add properties, and the properties show up in an inspector, and the properties, it knows the types of things. So if it's a string, it'll let you type anything. If it's a number, it'll have a number drop down in the UI editor. You could also use it for pretty printing structs and enums. This is handy for debugging and also for testing. Rust has derived debug, which basically codifies this in the language, but you can write your own thing in C++. And you could also do this stuff for serialization and deserialization of your structs into whatever format you want. You can also generate language bindings from your C++ code. There's a lot of tools like Swig that you use a different language, like a custom language, to define your interfaces, and it generates C++ code and it generates Python code and whatever. But you could do it the other way. You can make C++ code the source of truth and then generate the other languages from the C++ code. Tools like PyBind 11 do this for you using template metaprogramming, but the problem with that is you don't get to see what the generated code is, and it sucks to step through it in a debugger. If you generate source code, it's easier to step through, and it's easier to notice when things change in the bindings. And you could also use reflection to like see like comments or attributes on struct members. So if you have a command line parser, for example, you can annotate all your parsed variables with like help documentation. And then you have a tool that extracts all those comments or the attributes and generates -- help output. And I mean, there's probably plenty of other uses for this technique, but there you go. Anybody have questions? Oh yeah, applause. Yes. Yep.
Hi. You mentioned using libclang, that one of the downsides is, you have to build this utility and run the utility on the developer machine.
Yes.
And that has issues with cross compilation and such.
Yes.
But using regular expressions don't you have kind of the same issue because you have
Yes.
to build a utility? So
yes, with regular expressions, you have some of the problems that you have with libclang, but with regular expressions, you can do that in like a scripting language. You don't have to use a C++ compiler. Now, you can use libclang from Python, for example, but then you have to deal with a bunch of other issues with libclang too. But yeah, I've seen people use like shell scripts or Python scripts to generate code, well, parse with regexes and generate code.
Yes, that's a nice example, which shows that we really need some C++ reflection and codegen natively in C++.
Yes.
So have you looked at, for example, if you had used circle extensions to C++?
I am not familiar with Sickle. It's SYCL, right?
No.
Circle. Oh.
SIRCLE from Sean Baxter, which is
yeah. So
open source.
The Circle compiler and language adds a lot of reflection capabilities. I don't know about code generation. I have not used Circle because it's closed source, and that's a turnoff for me. And also, I'm trying to make something that people use. Like what I learned here is from a production compiler, not a C++ compiler, but it's from a real project. And that real project, I don't want to use experimental compilers like Circle. I did not research using Circle. I've been interested in Circle because they claim because they have more advanced reflection capabilities, they don't have to do as many hacks, so they can really improve compile times. So that's interesting to me, but I don't know about if it unlocks new features. I don't know what features it would unlock. It probably does. I don't know.
Thank you for nice talk. So in libclang and the regex example, did you use anything fancy for actual C++ code generation, or was it just prints?
Yeah, for the code generation bit, it's just print. Like in the production code, I don't use std print because I don't have C++ 20 or 23 or whatever. But yeah, it's just printing and then string interpolation. In the production version, I use in the production version, I need to care about Unicode escapes and stuff because reasons. Because I'm in the production version, I'm not just generating C++ code. I'm generating like translation files and some other things. And those I need to make sure the escaping is correct for the different languages I'm emitting. So like if you generate a Rust source code, then your printing has to be a little more sophisticated because it can't assume that the like \b works the same in the different languages. But yeah, it's just printing. And there's some command line parsing because I generate a header file and a CPP file, right? There's some other stuff.
So can you elaborate a little bit on the bindings or deserialization? I mean, I can't make the leap from being able to find a struct because of a prefix and then going to an attribute to actually walking the fields of the struct itself.
You want to know how to walk the fields of a struct, or?
Yeah, I mean, how would one achieve point number 3 or the second last thing, which is bindings or deserialization?
I mean, it's up to you what you do for language bindings. So like you would need to define the mapping yourself. So like I don't think there's any off-the-shelf tools that say, okay, an int in C++ is I32 in Rust or whatever.
I'm not asking the translation. That obviously needs to be done on language basis, obviously.
Okay.
What I meant was, how are we walking the fields of the struct itself?
How are we walking the fields? So libclang has a cursor API. You say, libclang, tell me about the stuff inside this thing. So you give it a thing. It could be a whole file, or it could be a struct you got from someplace else. And then you give it a callback function, and it calls your callback function over and over again for each thing. And you could say, I want to know more about the thing. So if you have nested classes, for example, if you ask for the outer class, it'll tell you about the inner class, and you can say, yeah, tell me about things inside the inner class, or just skip over the class and go to the next thing. The cursor API is like a recursive.
I say we are just walking the AST at this.
Yeah, it walks the AST. Well, not the whole AST, apparently, but it walks enough for some use cases. Yeah, I'm making it's a tool called QuickLint.js. It's a JavaScript parser linter. And eventually I'll have a type checker and code fixes and stuff. It's supposed to be an editor plugin that checks your JavaScript code. It's oriented for beginners of JavaScript. So it tries to be really easy to install, have low config operations. And it's designed to be fast, hence the name QuickLint.js. So a lot of the things I talked about incorporated in the compiler, but there's tons more. For example, a lot of I very carefully designed a bunch of the data structures to be compact. In this example, we generated a bunch of virtual functions. I don't do that in the production compiler because then the vtables will be very big. So instead, I have some more complicated routing thing. I also, instead of generating a bunch of methods, actually, it's using data tables. So it's a bit slower at runtime to scan the data tables, but it generates much smaller programs. And part of that's because the QuickLint.js compiler runs in a web browser, or there's an option to run in a web browser, and I didn't want to have like 10 megabytes of download. just because C++ templates and macros generate a bazillion lines of code. So I use more data tables, and they're very compressed. They're bit packed and all that fun stuff.
Right. Okay, so just to stop the slander against Clang, the reason I think it doesn't give you an AST is because it's not defined to be parsable. Like the contents of an attribute is just a random token soup.
Right.
Like,
So
and
the body of an attribute, there is some regularity to the body of these attributes. So in a C++ attribute, the parentheses must be balanced, for example. And like a string literal can't be, it has to be closed. It has to be open and closed. You can't have like an open-ended string literal. So there's some constraints. They have to be valid tokens. So you're right that you're right that it could be whatever inside, but in practice, there is some regularity to it. So it could give you the structure. It could parse the structure. Like it's basically parentheses, parsing parentheses and giving you like, oh, this is a list of strings or whatever. But the main problem isn't that it doesn't give me details inside. The main problem is it's as if the attributes were commented out or they weren't there at all. Like libclang doesn't expose them at all. It doesn't tell me the start and the end of each attribute. They just don't exist. So I have to tokenize the entire struct and extract the things inside the struct. That's another reason I put the attributes inside the struct, not outside. Like I could do the semicolon hack outside the struct. But then I wouldn't, when I asked libclang to tokenize, it wouldn't find them. I would have to tokenize the entire file, and I don't want to parse the entire file.
Thank you so much for talk. I have two questions. One is on a high level of reflection, the word itself. Like I followed through the examples and some use cases that are listed in your last slides, but on a higher level, like what defines a reflection?
What was the question?
What's the definition of the reflection just by itself?
My definition of reflection is a program that looks at itself. So in this case, it'd be, well, it doesn't have to look at the line of code that's running, but it looks at other parts of the program. So here I would have one part of my code looks at this this struct and extracts information from, like it sees each attribute, for example. So it's looking at the code, It's not looking at the generated code like the compiled code. It's looking at more of the source code. That's how I view reflection. Or in the example where we used concepts to detect if a method exists, that's looking at the code for the class and seeing, is there a method available?
Oh, thank you. And the second question is, can you give a brief example on the serialization, deserialization use cases?
Serialization, deserialization. I see this all the time in code that interacts with the web. So you might need to access some web API to, I don't know, get the weather or whatever. And it gives you back some JSON data. Now that's it's a string. You need to extract the information from the string. You have to extract the city from the string and the current temperature and maybe an array of historical data. You would like to, in your program, instead of dealing with a JSON string, you want to deal with a vector of ints or a vector of floats for all the historical temperature data and an std string for the city name or whatever. So it'd be nice to say, hey, JSON thing, convert whatever I get from the wire, from the API into my struct, right? And the names of all your fields in the struct would match the wire protocol. This happens, this is very popular in Go and also in Rust. And it's not that popular in C++ because we don't have these tools. At least they're not readily available, but you can write the tools. I've seen game developers do this for their, for like saving and loading levels and saving and loading like user saves. So That's usually with a binary format, not a textual format. So you want to enumerate all of the, for example, you would enumerate all of your things, all of the members in your class. And if there's a pointer, follow that pointer, serialize all those things, you know. I mean, it's up to you what you do with the serialization and deserialization exactly, but it's pretty common if you're talking with other systems or doing persistence or something.
Hi. I'm wondering why you decided to kind of encode your DSL, in this case, using C++ and not just use like a JSON file or something.
Uh-huh.
You know, so much of it is generated. You could have just put it all in a JSON.
Yeah. So why not use a JSON file for or some other language than C++, because that would be easier to parse? Well, the thing is, this was an evolutionary process. It didn't evolve exactly as I did in the slides, but like, you know, mostly it's historical reasons why I chose to go with C++. Another advantage of C++ is that it's C++ code which matches all the other code in your system. So if I look at some existing, so let's say I'm a new contributor to the project and I want to add a new diagnostic. Well, I'm going to look at existing code in the analyzer or the parser or something and see how they do it, right? So I want to go to, you know, I skim the code and I see, oh, there's a report error function, a call to report. And then it gives a diag unused var, right? I could just say go to definition and get C++ code. If it was some generated thing, I would go to definition and get some generated code, and I would say, well, maybe I don't even know it's generated code, so I edit the generated code, and then that's not good because it's going to get overwritten or something when I recompile. But like, it's kind of like, if you do this technique where the source of truth is C++ code, it leaves more breadcrumbs, and it's more obvious to new contributors where to put the code. And also, I don't have to learn a new syntax. Like, if you're working on Quicklin.js, you're probably familiar with JavaScript and JSON because there's a JavaScript tool. But I mean, if you're not working in, you have to pick something that the developer would understand. And I think C++ is probably easy to understand if you're working in C++ code. I mean, it's going to look weird seeing all these attributes. Like it's not normal to see a bunch of attributes on some code, but at least you know where to edit the code, and you can probably just copy paste it after you do the go to definition. You copy paste, and you're like, this is obvious.
All right, everybody, let's say thank you for Strager. Great talk.